Okay, so another thing worth pointing out about this quasi-set of y such that phi is that if we just suppose that this phi here just has only one free variable, which is y, then that variable actually becomes bound in this expression. So this doesn't really have any free variables. So we can talk about its interpretation without talking about any variables because it doesn't have any free variables. In that case, the interpretation of this is just going to be as an arrow from 1 to omega to the power of a. Now, alternatively, we could interpret this thing over a variable v of type 1. And if you think about the superfluous variable lemma or the substitution lemma, you realize that really this is just the same thing as the above, just composed with an identity arrow from 1 to 1. But in this context, we'd be rewriting this as the transpose of the interpretation of phi over v, which is a variable of type 1, and y, which is a variable of type b. And in that case, I mean, if we just think about what's inside here, we've got 1 times b. So that I'm not thinking about the transpose, but I'm thinking about what's inside of it. So then we have the interpretation of phi over v and y, which is going to be an arrow from 1 times b to omega. But then if we just took phi and just interpreted it over y, that would of course be an arrow from b to omega. But you can see that doing this interpretation of phi after p2 here is going to give us this. Okay, and this is interesting because we then see that what this thing in curly brackets is interpreted over this variable v of type 1 is the transpose of this kind of blue diagonal arrow like this, which we can write as the interpretation of phi over y after p2, which and that's transposed. So basically this is what we might call the name of the interpretation of phi over y. So we have this connection with other kinds of considerations we've had about exponential objects. Anyway, I just thought I should point that out. Now, what I want to do next is to introduce another kind of idea that's going to be useful for us for thinking about products and co-products and how to create them. So let's revisit the comprehension axiom. Now there's a sort of general one for exponential objects, but let's look at the version of it which is specific for power objects. It's not really, it doesn't really have any new content, but it's just sort of written in this language using curly brackets and in symbols instead of evaluation symbols and so on. And so here's the axiom. It says that it's always true that y is in the quasi-set of y such that phi, if and only if phi, where here y is a variable of type A and phi is any formula. So I thought it's worthwhile to actually revisit why this is actually true, okay? Because it is a little bit cryptic. So let's have another look. So firstly, we'll let x overline denote this product of objects capital X1 times capital X2 all the way up to capital Xn. And the first thing here is that this is a bit of a no-no in that, I mean, really this is going to get bound to a lambda operator, but we're going to have to interpret this whole term over some list of variables which includes y, and then we're going to actually have to change the name of this y to some other variable. So we're going to change the name of this y to some other variable y dash, which is also of type A and which doesn't appear in the list of variables which we have to interpret this term over. And so this is one of the notes about interpreting things involving lambda symbols. Like if you're interested to see it specifically, you can look on page 127 of McClarty's book. But anyway, basically we should rewrite this to say that it's true that y is in y dash, that y is in curly brackets, that y is in the quasi-set of y dash such that phi, if and only if phi. So it's this kind of thing of making up a different name of a dummy variable, basically, because our other variable agrees with it. And it's a bit daft, in fact, that this comes in the first place. But anyway, so basically, this thing which we're claiming is true, this comprehension axiom, it holds if and only if it's true that y is in the quasi-set of y dash such that phi is equal to phi. That when we do the interpretation of that over all of its free variables, let's say this list of free variables x overlined and together with y, that's going to send everything to true. And this is basically going to hold when the interpretation of this stuff on the left is the interpretation of phi over x overlined and y. So let's work out what that is. So we're interested in what's the interpretation of y in the quasi-set of y dash such that phi, where we're interpreting over x overlined and y. And so we just undo our kind of abbreviations. We see that this is the interpretation of E after lambda y of phi, comma y, interpreted over x overlined and y. And so we can work out this as E after the transpose of the interpretation of phi over x overlined y and y dash, comma Pn plus 1. And now you can see from this diagram, which commutes, that this is actually just going to be the interpretation of phi over x overline, comma y dash after identity arrow of x overline times a, comma Pn plus 1. Because this diagram commutes, basically. So, I mean, we're really interested in calculating the composition of these two blue arrows. And because this diagram commutes, this is the composition of these lower blue arrows down here. But also, by the kind of superfluous variable lemma, I mean, here we have the interpretation of phi over x overlined, comma y dash, but you see the way I've bracketed these things off, like it's as if this is really just coming out of these two different objects here. So if we instead do P1, that just grabs the x overlined and the a, which is all that this phi really does depend on, because I've already said up here that it doesn't depend on y dash. Yeah, it doesn't. So we know that phi doesn't, well, by our replacement rule, we know that phi doesn't depend on y dash. So we can just write that this thing here is equal to interpretation of phi over x overline, comma y after P1, which is just grabbing this first part here. So we can rewrite this as interpretation of phi over x overline, comma y after P1, after identity arrow of x overline times a, comma Pn plus 1, here x overlined is just a product like this, which are the relative types of the little xi's. Anyway, and we can see that this is just going to equal the interpretation of phi over x over line comma y. And that basically proves our result, because we've basically shown that when we interpret this, it gives the same interpretation of this. So yes, it's true that this is equal this. So yeah, this all works out. So that's a very, very fast sort of proof of the comprehension axiom. Now, how are we going to apply it? Well, firstly, I'm just going to rewrite it a little bit. So I said it like this before, where y is variable of type A, and we've got this sort of bound variable y dash of type A as well. Now I'm just calling the variables x and v, but they're both still of type A. And phi, of course, is any formula. So now we're going to use this idea when phi is false. So this gives us that, well, one of the implications of using this comprehension axiom is then that x is in the quasi-set of V such that false implies false. And then we can use the implies rule. So we can sort of take these curly brackets to the right-hand side of a double dot and put an implies there, and take all the stuff to the right-hand side, in fact. Well, in fact, this is just a straightforward application of the not rule to go from the top line to the bottom line. So we essentially have that it's always true that not x, we basically have that it's always true that x is not in this quasi-set of V and A such that false, okay? Which basically makes sense. It's a fancy way of saying that this is like an empty subset of A, basically. In here, of course, x is a variable of type capital A. Anyway, so we have this. This is one of the things we want, that it's not true that x is in this quasi-set of V such that false. Now, we carry on. Let's define an arrow, which we'll call naught A, which is an arrow from 1 to omega to the power of A. And as an arrow, we'll define it to be the interpretation of the set of V in A such that false. Okay? And now, of course, what we have is that it's going to be true. Like, so that's how we think of naught A as an arrow. But since naught A is really just a sort of arrow from a terminal object into a particular object, we can also think of it as a kind of constant term. And so we can then say, well, is naught A equal to the quasi-set of V such that false? And yes, it is. Okay, because if we interpret these over their list of free variables, which is actually the empty list, we see that they're the same arrow. Okay, so that means the equalizer is the maximal subobject. That means this is a true formula, and so on. Okay then. So here's the next part, and this is actually fairly trivial in a sense. Sort of, if we apply a bit of common sense, it's fairly trivial. So what we're basically saying is that it's true that naught A is equal to this set of V such that false, and it's true that we won't have any X in this set of V such that false. So our conclusion is going to be that it's true that we won't have any X in naught A. In other words, we want to get at this. We want to get at that not X in naught A. And it's pretty clear that that's going to follow from these two things. But what we're going to do now is establish this rigorously. And this is cool because this is a standard kind of very, well, I don't know about standard, but it's a very useful trick because it comes up a lot in dealing with the Mitchell-Benerbauer language. So here's how we do it. We're going to use the substitution and equality rules, and what we can get is that for any formula psi and for any variable z of type B, and terms alpha and beta of type B, which are free to replace z in psi, we have this, that alpha equals beta and psi with z replaced with alpha always implies psi with z replaced with beta. Okay, so what we're going to do now is we're going to use this idea. So basically you can get this from using the substitution rule and the equality axiom 2 from the so-called axioms of local set theory. Anyway, using this idea, let's use this idea when our sort of object or our type of interest is omega to the power of A. And so we've got z of type omega to the power of A. And then suppose that the formula psi here is not x in z. And here x is of type A. And also let's suppose that alpha is this term 0a, which indeed has type omega to the power of A, and also beta is this term, the set of V, well, the quasi-set of V such that false. Okay, so now we have a sort of version of this in this special case, and it looks like this. We have that since this is true, we have that from nothing, we have that saying that the quasi-set of V such that false equals 0a, and taking this not x is in z and replacing the z with this quasi-set of V such that false is going to imply what we get if we take this not x in z and replace for z with naught a. So just making that replacement, then we end up getting that the quasi-set of V such that false equals naught a, and not x in the quasi-set of V such that false always implies not x in naught a. So basically that is a sort of universally true thing because we got it from no assumptions. But also note now that we have that, well, let's just correct this a second. Okay. Okay, cool. Right, so basically we have this as universally correct, but also we've already sort of shown that the quasi-set of V such that false, we've already shown that it's always true that the quasi-set of V such that false is equal to naught A, and we've also shown that it's always true that not X in the quasi-set of V such that false, here in both, we always have, of course, X's of type A. And so it follows then that this is true and this is true. So it's always true that the set of V such that false is equal to naught A and not X in the quasi-set of V such that false. Okay. And so now, since from nothing we can get this conclusion, and then that this conclusion in turn implies that not X in naught A, then we get from nothing not X in naught A, because clearly every variable which is free in here, as in just the X of type A, is also free in here. So we can use the simplified cut rule. So we get this, that not X is in naught A, where X is of type A. That's what we wanted.